Mujde, the floor is yours, and we'll see you on the other side.
Right. Thank you. So I will basically briefly talk about anomaly detection and its application areas, how to identify anomalies and challenges in anomaly detection, machine learning methods for anomaly detection, a practical example I will give, and there is a summary and useful links. So basically, anomaly detection is finding observations in data which are actually not normal, or they are different than expected behavior. They are generally rare or uncommon events, and sometimes they are discovered by basic statistical rules as well. So they are generally statistically significantly different from the other observations. In terms of machine learning terms, they are generally unsupervised because it's really very difficult to find labeled data, especially if it is time series. But there are also supervised cases like fraud, if it is labeled, of course. Generally, anomaly detection models support decision-making process in business. Although I believe, like, especially if it is real-time decision-making, is always good that it supports, but the people do not really only rely on automated decision-making. Some application areas are like system health monitoring. I have previously worked on like predictive maintenance and also, again, health monitoring of flying systems. They are also used in medical diagnosis, network security, defect detection in images and manufacturing, basically, cyber security and fraud detection, and many more, obviously, that I don't know. Basically, I mean, people are, I mean, in my experience, are used to looking at anomalies visually and just try to identify them, like looking at this figure, this looks like an anomaly if it is really beyond the variance of the signal itself. I mean, when it is univariate or bivariate, basically, it may be easy to identify those visually, but in multi-dimensions, it's much more difficult. So we need some techniques to do that. And they are also sometimes called as outliers. And statistically also, they are observed in box plots. And there's a method like this IQR range method, basically, when the observations lie beyond this 1.5 interquartile range, then they are called as anomalies. Again, this is a simple approach. So beyond those points, we call them abnormal. Similar to the interquartile range method, there is also standard deviation method. So we say, like, when the observations are beyond the mean plus minus 3 standard deviations, then we call them outliers, or they are abnormal. So two of the methods I mentioned are really simple statistical methods. They are used like in Six Sigma methodologies as well. So they rely on the fact that observations which are far from the rest of the observations, or center of mass of observations, they are called outliers. That's easy to detect when we have 1 or 2 variables, but or when we can visualize them in a histogram or scatter plot or a box plot, but it's challenging in high dimensional feature space. It's also sort of defined as, like, if based on historical data, if we have some expected behavior, so if our model learns the historically not labeled but historically known as normal data, and if it is expecting such a behavior, and if our behavior, if the actual observations are different than the expected behavior, within some confidence interval, then we also call them as anomalies. So there's a nice link over here, just to see if we can identify anomalies by eye all the time. Here it looks like, I don't know, it looks like anomaly here to me, which is correct. I haven't memorized the answers right away. I'm just looking. But here it is more difficult to identify. Maybe here, I don't know. No, I'm wrong. It's here. So it's difficult. I mean, in this case, it's really almost impossible to visually identify such anomalies. Here, maybe here. No, there was no anomaly in that one. Okay, so here, perhaps here, yes, here one, and there is one more here. So possibly the model is learning the periodicity of the signal and the trend of the signal, and because this behavior is not matching with the expected behavior, they are labeled, they are identified as anomalies. And this one may be here. Yeah, it looks like it's here. So, I mean, here basically I want to show like it is not always that easy to identify, especially multi-dimensions, and especially if the signal has some periodicity and some trend, it's not very easy to identify them by visualizing the data. So challenges is basically defining what is normal is challenging, because I mean, today something can be normal, but tomorrow it can change. Think it like, for example, if we are looking at customer behavior and we are looking into like fraud as abnormal behavior, today's customer profile may be different than tomorrow's customer profile. Therefore, it's important that once we train our model on the normal behavior, it's generally good to check if it is working okay, and it is generally very likely that we need to update our models with incoming customers. As usual, sufficient number of training and validation data set is important, especially maybe this is important when it is supervised, because generally these events are like in fraud are very rare events. So it's important that we have got a good representation of our data. It's important that we have got exploratory features, sufficient number of features. And we need to be careful of high dimension space, as I mentioned, that's challenging. Noise in data is really important. I have experienced that myself as well, because we don't really want, I mean, once we get our basically data from sensors especially, it's impossible that it's not noisy. So there's always noise in data, but obviously we don't want our model to learn this noise as well. So at that point, actually, in my experience, we were coming together with field experts and we were trying to filter that noise before we feed them into the model. But I mean, we should filter in a way that shouldn't cause any lag in the response. So at that point, really using a proper filtering approach and coming together with field experts is very important. When it's a time series problem, short time series is challenging because I mean the model doesn't have too much to learn. But on the other hand, if it is, I will show some examples. If it is like different vehicle rides, they are all short rides. We need to find the way to combine them because basically it's not a long time series, but we have got many short time series at hand. So we need to find a way to sort of combine them. And I will show an example to you in that. Importance of data preprocessing is really important in terms of features. And as I said, like in terms of cleaning the data and stuff like that. And here, detecting anomalies in real time is really challenging. And in my experience, people are generally do not solely rely on automated decision made by the models, but they are generally used to support decision makers in the business, which makes, I think, sense to be on the safe side. Importance of data processing, an example could be like, for example, if we have a customer segmentation that we have already done on customers, maybe using k-means clustering or in terms of demographics and basically spending behavior of customers. We have different segments of customers, and if we, let's say, want to develop a fraud model on this, we may not, we need to investigate, because one model may not work well for each segment because their behaviors may be different. So we need to test different basically models for different clusters in the data. Short time series like this it was like one of the examples I found very challenging when I was working for basically health monitoring of flights in missiles. It doesn't matter, it could be any vehicle basically, and imagine that these are just acceleration measurements. And we somehow know that these are like normal behaviors, so these are healthy rights. So how do we know it? We basically rely on the field experts' knowledge on that, because they physically know that the rights were okay. So when we have many rights like that, how could we train our model to learn the normal behavior, normal acceleration behavior? Can we like train models for each right separately? Which doesn't seem very reasonable when we have too many rights, and how we are going to combine them. Can we combine the rights just one after another? Well, we need to be really very careful in that, because we need to find a method to tell the machine learning model that this part, the second right, is not the continuation of the first right. So at this point, we should tell the model that this right is finished, so just mask those values and another right starts again from here. So basically, our models should learn that each of them are separate rights. They are not following each other. And important thing is that, as I said, we should not learn noise. So we should feed filtered data in our models.
Mujde, I had really similar curves with photodiodes from robotic arms in a factory. They were collecting sensor data, and they really look like this. And I mean, in sensor data, I guess this is quite common.
Yeah, I mean, noisy data is very common when we have sensor data. But I mean, that's why really data preprocessing is very important, to find a good filter which doesn't lead any lag in response, and smooths our basically signal in a sufficient way, I would say. Shall I move on?
Yeah. Thanks.
So if we are lucky and our data is labeled, which is almost impossible in time series data, but maybe some tabular data, then we are lucky and we could basically use any classification technique like logistic regression, decision trees, random forest, XGBoost, SVMs. But we need to be careful about imbalanced data sets in this case, in terms of two things, basically, maybe in terms of performance measurement metrics of the basically model, and also in terms of sometimes people do like upsampling or downsampling methods to basically get rid of this imbalanced data set, which is very typical in fraud as well. For many cases, anomalies are not really known in advance. So we have got also semi-supervised anomaly detection. Again, there are no labels, but at least we know that our training data consists of normal data. I mean, our field experts come to us and say, okay, just basically train your models on those signals. We know that physically those rights were okay. Once we know that there are no anomalies in the training data set, then we are happy. And in that case, we basically train our model on healthy data, on nominal data, and then we detect anomalies basically once the observations are deviated from the learned normal behavior. I'm sure there are many more methods, but the ones I used, not all of them I have used, but LSTM, like deep learning, basically a deep learning method to remember long-running dependencies, especially in time series, LSTM autoencoders, ARIMA, SARIMA, and WAR models to predict expected normal behavior in time series. And there are HDM models as well, which I haven't used before. But I mean, the idea is all similar because they are basically assuming that data is normal, even if it is in multi-dimensional space. They are basically learning the time series dependencies so that we can expect, we can sort of learn what to expect from upcoming data. There are obviously unsupervised anomaly detection models, and these methods rely on distances and densities generally. And the methods are rule-based approaches, as I mentioned before, like the interquartile range method, standard deviation method on histograms, but they are generally suitable for univariate analysis, and they are also suitable for unimodal distributions, but they are not as good when we have like bimodal distributions like that. We can also use clustering methods, dbScan, k-means for the same purpose. There are also other density-based techniques, k-nearest neighbor, local outlier factor, isolation forest, SVM, and there are many more actually. Bayesian networks are also used in anomaly detection. For this basically presentation, I wanted to focus on one of them. I think the semi-supervised ones are also important, based on the time series prediction ones, but that's a deeper subject. Maybe we can discuss on another call. It's a little bit more detailed. Isolation forests are basically, they are like random forests, and they are built using decision trees. They are implemented in unsupervised fashions because there are no labels. Basically, it's just like random forest. It's again ensemble of trees. The assumption behind is that anomalies are outliers and they are really fewer distinct points so that they can be isolated easily. So the assumption is based on that. So it basically randomly splits the observations and takes each point and basically finds the sort of number of steps to isolate the point. So the sooner the point isolates, the more likely that it is an outlier or anomaly. Like, for example, in this case, if we have a split from here and one more here and one more here, we can easily sort of isolate our point. And in that case, we would say, okay, we in random many different splits, in average, we could get to this point, isolate that point in about like 3 steps. But if it iterates through this point, I mean, if it just tries to find the label for this point, then it will take more steps, obviously, because I mean, it's not as isolated like the other case. So in that respect, number of splits would be much higher than the previous one. Once that number is much lower, then it is more likely that this is an outlier or this is basically an anomaly. So the idea behind is that this one. So I just have a notebook for that. So basically, I have used this Swiss banknote data set, which has got these features basically. And we have got a label, but this label is just to double check ourselves. We are not going to do any classification in that respect. We are just going to basically test our unsupervised approach here. So our basically this feature says like this banknote is fake one or a genuine one. So this is a little bit modified version of the Swiss banknote data set. So we just read through this data, and it doesn't have too many features anyway. And once we look into the sort of the this counterfeit value counts, it's about like 32% of our data is, I would say, like fake, which is not really too imbalanced in that case. But there would be cases which could be like 10%, even 5%, which we would approach differently, maybe upsample or downsample the zero cases. So if you just simply look at the interquartile range method to detect outliers, basically, and this is our X features, dimensions, basically, left, length, right bottom dimensions. So what I'm doing is here, basically, I'm looping over the features, and I'm getting the low and higher quartiles limits. And once the observations are beyond those limits, I'm basically labeling them as outlier here, or as an anomaly here. And once I basically plot the box plots, I see that there are these outliers here. These are visually easy to identify, especially in one dimension like this. Then, so basically what I'm doing here is then, okay, I have set my outliers. So if I look at the cross table between those actual values and what I have identified as outlier without using those labels, I see that these are my like true positives and true negatives and stuff like that. So just I'm looking at all accuracy all performance metrics mostly, and just to basically explain people better, maybe the students, I just use the formulations myself, and only looking at the interquartile range method, we get an accuracy of about like 67%. And here, I want to also look at the histograms as well. I mean, this looks normal, not too bad. I mean, but here, for example, these are like bimodal distributions. So I'm sure I can do better than IQR range method.
Sometimes sorry, Mujde, sometimes these IQR methods, histogram methods, or let's call them simple methods, they can really create miracles.
Yes,
People,
yes, they can.
some people are really not familiar with these things, and you know, if you are onboarded to a project in a factory or in a company, and you know they want you to do this kind of anomaly detection, and I guess this is, as you are very, very well presenting, this is the first step to take.
Yeah.
First do the simple thing. Maybe they are already happy, and you are 80% done.
Easier. Yeah, and it is okay, but I mean, it is okay to look into such things like in one dimension and stuff just to visually understand what's happening. But in multi-dimensions, and if there is a time series component, then they are not helpful in that respect. So we had about like 67% accuracy, not too bad. And if we use this same data, if you use the isolation forest, training and test split basically, So there are some factors that you could play, like the contamination factor is basically sort of how many percentage of the data you are expecting an anomaly kind of information. So, and number of estimators is basically just like in random forest, is like about ensembling how many trees you are going to use. So you can again play with those parameters. So we do our prediction. We fit our data to the training set. We do our prediction. And basically then I'm just adding another column as identified outliers by this method, basically. So when I basically train this model, so I get labels as 0 and 1. Actually not 0 and 1, 1 and -1. Here actually -1 means outlier. So to make it similar to my data frame, if it is -1, I say it is fake. And if it is 1, I say it's not fake. So that I can basically compare this with our actual labels. So looking and comparing this with our actual labels, then I get this cross table. And looking at the accuracy of the results in the training data set, I go up to like 82%, which is better than the our simplest approach. And I do the same thing on my test data, and I get about like, again, 80%, 78%. We could do some really manipulation to decrease the overfit, but overall we can say isolation forest is better, is doing better in that case than the IQR method. And finally, I wanted to use like DB scan, and just again, we can play with this epsilon and minimum samples parameters, and I get my labels like this. And again, when it is -1, I call it outlier, and when it is not -1, I call it as basically a genuine banknote. So I just mentioned it here. And when I look at the cross table here, then accuracies and other stuff, I see that I get a 70% of accuracy in my outlier detection. So overall, it looks like isolation forest was the best in this analysis in terms of performance metrics. And DB scan again did better than some statistical simple rules. There are many other methods that we could study, and really the approach to the time series is totally different, but that's really another subject to go over. And finally, if I need to summarize my points. So anomaly detection methods basically should be selected based on the data content, if they have got any time component involved, if it is univariate, multivariate analysis, our feature dimension space, is it supervised or unsupervised, or somehow do we have got like a non-normal data like in semi-supervised case. We need to look at the distributions. Field expertise is really very important because they physically know what is normal behavior, so they know what to expect as normal. So we need to come together with field experts and before the modeling stage to select the nominal data, healthy data, discuss on noise removal strategy and stuff like that. And after modeling stage, again, we need to come together and say, okay, these are my predictions for anomalies. Do they make any business sense, or physically are they reasonable, kind of thing. And data preprocessing is really important, as always. And again, if we are doing real-time anomaly detection, then we need to be really careful to be on the safe side. So that's all from my side. If you have got any questions, I'm happy to answer.
How many questions is a good question I have? Many.
Okay.
But thank you so much, Mujde, for sharing all that. It's fascinating stuff. I think honestly, one big question that I have is, given that Swiss banknote data set, what would the can you tie it together for me as what's the final product, and how does in those three examples that you had, and let's take the isolation forest, which was the best, what now what, like, how does, based on that, what is can you basically explain the final result from in the best case, the isolation forest, and what that actually allows us to predict or forecast, and how that would be useful in the Swiss banknote sense? Does that make sense?
I mean, Swiss banknotes, I mean, I'm not very familiar with the subject, but I mean, maybe I could give an example from my experience. Like, for example, when we were doing predictive maintenance for flights for GE engines, basically, we were identifying those anomalies, and we were saying, we were using Bayesian networks by that time, but anyway, we were saying like, daily we were getting all the data and looking at the data and feeding them into the model. We were saying like, okay, there is a 75% probability that this engine is faulty, kind of information, and we were sending this information back to airline operations center. And in that case, that was basically the objective was to identify the faults before they actually happened, so that, I mean, no accidents could happen, or like maintenance costs would be solved and stuff like that. For example, when I was doing for like missile flights, sometimes when things are getting wrong and system health monitoring gives you some alerts, you need to take an action in real time. Even if not real time, because real time is risky, you can do this like offline. And this basically helps the field experts that, okay, there's an anomaly here. So there might be some problem in this flight, although you see like everything seems okay. So basically, we are identifying anomalies so that business can take action on that. Because anomalies are things generally businesses want to take action, like in fraud.
So in the, and that part makes sense conceptually, but for instance, could we take a look at the result of the isolation forest that you demonstrated?
Okay.
So this is the DB scan, and just to use the best example, right?
Best example. I think it was this one. This one, yeah.
There we go. And so can you just explain this result to us, kind of as simply as possible, if you don't mind? Like, for instance, up in top, you've got the labels outlier AF0, 1, and then for 0, you've got 25 and 4, and for 1, you've got 6 and 10.
All right, okay.
Like, what does this mean? Like, what are we showing here?
Okay, so basically here, what I am doing is, so these are my outliers. So these are, so I have got like 29 genuine banknotes here, they are actually genuine. And among those 25 genuine banknotes, so my model said 25 doesn't have any outliers, so they all look genuine too. So my model made a good prediction here.
Okay.
But among those 29 of them, my model said like 4 of them are actually anomaly where they were not.
Okay.
And so this obviously this is my sort of, if this is 0, so this is my false positive.
Right.
False positive.
Okay.
Confusion matrices are really always confusing. I need to remind myself.
That's why it
Yeah.
is called confusion matrix.
Because they're so
It always
confusing.
confuses me. But for
Yeah,
example,
the most important thing, I guess, first for the
Mhm.
students to grasp could be, in the x-axis, you are seeing the actuals, and in the y-axis, you are seeing your predictions.
yes, exactly. So in my actuals, like for example, I have got 16 fake banknotes, and among those 16 fake banknotes, I were able to identify 10 of them, and I was not able to identify 6 of them. So this basically all affects my accuracy and recall. Actually, I reminded that to myself in somewhere because I know I will always get confused about these things.
Yeah, those 6 cases are false negative, and they are more expensive,
Yes.
with cost, because you were not able to detect.
Yes.
And because they are fake banknotes, it creates, financial problems.
Yes.
Right.
False positives are like false fire alarms. You just go out and come back. There is no big deal.
Mm-hmm.
Like, for example, precision is here, like my true positive over true positive and false positive. So if I said like here, for example, in IQR method, I think, is it IQR method? I don't remember. So what is this? I said like, I think I put a wrong one in here, but basically true positive, which is here. Can I have a look at something? It should be.
I guess we were in the isolation forest output.
Was it?
Yes, we were talking about the isolation forest's confusion
Yes.
matrix.
I mean, yeah, so basically it's all about like accuracy is basically how well you are identifying the 0 cases and 1 cases. And accuracy is like that. But recall is like how well you are identifying the fake cases kind of thing. So therefore, I mean, as Gilad mentioned in the course, if your data is too imbalanced and if it is critical to give a decision, like as you said, Çağdaş, for example, okay, this is fake, but it's actually not fake, then you need to sort of give good decisions about which metrics to choose among those, accuracy, precision, and recall. And once your data is imbalanced, basically F-score is better to look at. I'm correct, right, Çağdaş? I'm getting confused.
Yeah, sure. Of course. This is really, I guess, maybe 3-day course. I mean, the whole confusion metrics and
yes.
Maybe together with logistic regression and some anomaly
Yeah.
detection. It can really take some time to digest. And
Yes.
I recommend to our students that, they should really spend time on confusion metrics because it is a real common interview question. I can't imagine a data science interview without confusion metrics.
I got it again. I again forgot the name of what I was talking about.
Interviewers also get confused during the interview, which is also common.
So can you, if Çağdaş, if you don't mind, or what would be a good example of an interview style question, related to the confusion matrix?
Yeah. So, for instance, a question could be, imagine that you are doing classification, you have a classification problem, and what would be your metric to understand your model's performance? Talk about your performance metrics when you are doing classification. So this is a common question, and the answer is confusion metrics. I check my confusion metrics, I check my accuracy, recall, and precision. And F-score is also a derivation of precision and recall. You just need to talk about these metrics.
Yes,
It's a common question. Yeah.
I also exactly got
I can
this
dig deeper.
question. Yeah, like for example, Charles, as you mentioned, I mean, that question came to me, and after that, just like in the course, as Gilad mentioned, then the interviewer asked me like, okay, you have got a, let's say, a cancer data set, and only 10% of the data is labeled as one. So only 10% of people are cancer. So he asked, like, in that case, like, accuracy is a good metric to use. I said no, because I learned from Gilad.
Yeah, it's
No,
a trap.
yeah, it's a trap, because in that case, for example, okay, just like in here, for example, you get the, I mean, let's say only from 100 data, you have got 7 cancer people. Even if you don't identify the cancer people well, you will still identify the non-cancer people well, but that's not enough for you to have a good model.
Yes, a good model should perform better than the majority case. If in your data set 98% of the data is okay, and 2% you have 2% anomaly, then you can just say all of them are okay and you are 98% right? And you can claim that I have 98% accuracy. You are the king, but it's not the case. That is the question, actually. That is a famous interview question they ask. You shouldn't be looking at the accuracy metric. You should be looking at the precision and recall metrics. And they are the ones in this confusion metrics she just showed, identifying how precise the model is capturing the actual cases, and also how precise it is identifying, when you predict anomaly, if it is really anomaly or not. Maybe the last part of my sentence was also a bit confusing, but the more important things are capturing, how many cases you are capturing from the total anomalies.
Yes. I think here I made a mistake. Let me have a look. For example, here I said, what's my precision score? My precision score is actually 25%. What's my true positives? My true positives is this, right?
Yeah, so this model is capturing only one.
Yes.
So there are 48 anomalies in total in the data set.
Yes,
and the model is capturing only
good.
one.
So this, you see, like, this is my IQR method, and my precision is not good because it's only capturing one of the actual fake banknotes.
Yes.
And my precision. So, but when the data is imbalanced, or when you are not happy with those accuracy, precision stuff, it's always good to look at the F-score, because F-score is sort of giving a balanced information on both precision and recall. If accuracy is not proper a metric for your problem, especially like in imbalanced data sets. So here we look like F-score is 3.92, which is really bad anyway. So if we go to like our isolation forest, for example, it gets much better.
Yeah, that's the real improvement. You improved the F-score from 3% to 66%. And could you go a bit up? Could you go a bit up to show us the matrix? Okay, stop. No. I mean the confusion matrix. Could you go a bit down?
Okay.
Yeah, this one. This one is the matrix. So in here we are capturing 19 anomalies.
Yes.
So we improved it from 1 case to 19 cases.
Yeah.
That's the metric we should be looking at.
I think to take it back to kind of where my mind goes oftentimes with this, which is the kind of how this information could help a business decision, right? Or in, let's say, a government decision. So let's say you've measured all, because the features of these banknotes are essentially the dimensions, right? And the physical attributes, like the width and the length and maybe the weight. And so given a sample of 1 million banknotes, when you analyze that data and you could come up with a you know, 81% accuracy or 66% F score,
Mhm.
there could be a spot where you say, we can predict that the entire, you know, let's say 100 million banknotes that are out there, this number of them are fraudulent or are counterfeit or fake. And at a certain threshold, the government could then say, okay, we need to update, we need to release like a new banknote or something. Is that about right?
I mean, it could be because I'm not a really very finance person. I'm not sure like what action they could take, but obviously once, I mean, they would like to know about like fake banknotes, or it could be the case like in, for example, exchange bureaus and stuff like that. They don't want to get like fake banknotes, and there should be some action to take when there is some anomaly. I think in business in that respect would know that better. Maybe Çağdaş, you can say, but it's a business decision.
And that just sounds logical, what Ryan just said.
Yes.
In finance industry, what I hear a lot is fraud detection. Based on the variables you have in your data, you predict if there is a fraud or not. Or credit risk scoring for individuals, for persons, for banking in banking industry. Would you give someone credit or not? And you maybe identify some persons, some strange transactions using some of these methods. Yeah, I mean,
So
Like in, for example, insurance field,
yeah.
they were trying to get this anomaly behavior so that they would sort of trying to capture fake claims. So in that respect, like they wouldn't renew their policies, or they wouldn't get that kind of customers just from the beginning when they apply for a product. So those kind of actions the business can take.
and then in the case of fraud detection, right, at a bank, let's say that and it's unsupervised, or you know, we're basically looking for real fraud, that cases of potential fraud in, let's say, transactions, and we want to then actually go you know, forward this outlier. How do we, based on from where we are here, how do we get back to the actual data point that we have detected as an anomaly?
Actual data point, I mean, in this code.
So we can think about Visa or MasterCard transactions, live streaming globally, huge operation.
Right.
All of a sudden, from your credit card, a huge amount was seen. You know, in your purchasing history, there is no such number. Actually, this is a simple model, but just to give an example. And then the action is immediately to block your credit card from the bank. And this actually happened to my wife.
Or notify the customer somehow. I mean,
yeah,
that kind of
yeah,
thing
yeah.
happened.
That's what I meant by fraud detection.
Yeah.
My experience was, as I said before, with robots, sensor data. And in that case, when the model detects anomaly in the signal, there were those signal curves like she showed. And the factory floor employees, they immediately stop and reset up the machine because the curve starts changing and it affects the car production. So that's another example I can give.
And sometimes it's like an early indication of a fault. So before a disaster accident would happen, you early detect it and you get the vehicle into the maintenance kind of thing. So it's an early detection of some drastic event, really.
So
Your
a little
model
bit,
is good enough.
if you scroll up just a little bit, and my apologies if these questions are too simple, but essentially in the code, when you detect the anomaly, essentially at that point, you could then, you know, write to a
Yes.
file or raise a flag or, you know, do whatever you need to do programmatically to
Yes.
address this potential anomaly.
Yes.
Got it.
Yes.
You
And
can,
when I,
yeah.
and basically when I find an anomaly according to my model predictions, I just add another column and label it as 1, and later on I can just call it back. So I know which data points are anomaly and I can get them back. I can log them.
Got it. Got it. Yeah. Nice.
So Scott had posted up something where he was saying he doesn't have a good enough understanding of these type of topics to ask an interesting question. Scott, I'm with you 100%. I feel like I'm drinking from the fire hose here. I know just enough to almost follow along with all this stuff. So yeah, this is a very you know, this is kind of a deep dive on the topic. You know, with you know, obviously, you know, Mujde, you're an expert. Shadash, you're an expert. So you guys, just listening to you guys talk, I'm actually getting a lot more, you know, off of it by listening to you guys go back and forth and some of the questions that are here. So, but one of the things that he says, and again, I'm going to parrot it here too. He says it's fascinating to see the variety of libraries and techniques that are used to analyze data and produce results. You know, going from some abstract glob of data to telling us something useful or enlightening, which is, you know, not going to be obvious without all this analysis that goes on. And so, you know, for folks who are seeing this afterwards, who are watching the YouTube video and are looking at this going, what the heck is this all about? Kind of go with it. This is all good stuff. And, you know, I don't need to understand it all right now. I can, you know, I may pick up something later and then all of a sudden I'm going to connect it back to what was talked about here. You know, this is all interesting stuff. I've done very little in the way of data analysis and certainly nothing to this depth. So this is, you know, very interesting and very, you know, very good to see all this stuff here. Especially for me, the big thing here is just the, you know, the use of the Jupyter Notebook to do all this analysis and just come up with all this stuff. So that's always lots of fun.
Yeah, actually, I had a plot as well. I would like to show that plot as well. But I mean, maybe because I'm not familiar with the tech talks, I don't know. Maybe was I too much into detail? I don't know how the content should be. Is it should be like?
You've done a fantastic job, Mujde.
I'd rather have too much. I'd rather have too much information than not enough.
Right,
Yeah.
okay.
So
I
I can.
I really need. I mean, even myself when I was explaining, I mean, Chadash, also you see, like I'm getting confused myself with those metrics and stuff. I mean, they really need some attention. But I think especially this accuracy bit, Gilad explained in the course very well.
There is something nice about these notebooks that I like. You can schedule them. You can write a clean notebook and you can schedule it to run every Monday evening, for instance. And then it can write the output CSV file to a folder where a data engineer can read it and use it in wherever they want. It can send it to a web server where you have a web application. It can look different, but notebooks can do that. Yeah.
Yeah. So, and now you can just automatically basically report. I'm just going to try something. Oh, did it work? I just copied it. Anyway, I mean, you can also like plot all this stuff and maybe in terms of different features. I basically tried to here like try to plot the anomalies which are basically here on top of my predictions, and they were mostly on top of each other, but anyway, it's difficult to show it here now because I got an error. And there are all sorts of things that you can do to visualize and to report the results to business. Obviously, this would not be something to report to business directly. Instead, you'll just show some charts. You will just mention about your accuracies and precisions, but in a way they could understand. I mean, this is like really a tech talk. It's not a very much into business representation, really.
Right.
It would be much of a summary then.
Oh yeah, I was just curious because that's the question I always have. Oh, in my mind, I'm always when we talk about the models and topics just like this, I'm always thinking, okay, with this, you know, what, and I'm trying to wrap my head around kind of what can happen next, right? And which helps it make sense in my head. But this has been fantastic, and you know, I'm with John and Scott, and that most of this is flying right over my head, but I'm kind of following along and thinking and seeing how interesting it is. And it really honestly makes me want to dive further into it. And you know, basically for the person that's really interested in this and it's flying over their head, both Mujde and Shadas, what would you recommend as good next steps for that person who's just watched this, is really interested, doesn't fully understand what's happening here, but wants to be able to, like, what are some good next steps for them to take?
Just get
Let's
in
say the
touch with
person
us.
already knows Python. Yeah, get in touch with us. That's a great answer.
Get in touch with them. I mean, I have also like given lots of resources, but Anomaly Detect, I mean, just by the name suggests, I think in general, it could be things like anomaly is something that we don't want. Anomaly is something that is not expected. And when the business doesn't like unexpected things, and business wants to sort of alert beforehand the anomaly happens, and they want to take action. And because they can't really do this visually all the time and in time and all in this feature dimension space, we need to find a way to report them. Hey, this looks like an anomaly. You may have a look and take an action, kind of thing. But I mean, if they are into that, there are really many resources, and there are many methods. They can just start with like one of the, I mean, I don't know, one of them to start with those techniques. Where are they? Machine learning techniques. There are many. I mean, they could, if they are interested more into those like time series problems, these are the ones to go ahead. I mean, they can do like time series anomaly detection. They can just read articles and stuff like that. I mean, there are lots of things on the web, so and they can always get in touch. I don't know.
The next step would be getting really comfortable with central limit theorem, basic statistics, how to understand the standard normal curve, and how to identify differences in your data in using basic statistics. So that is the key, I guess, to 80% of the problems out there. Yeah, this one. So this can really solve a lot of problems. This can be a next step for the students to.
Also, I mean, sometimes the objective is not really anomaly detection, but sometimes we are just building up a different model for different purpose. But even in that case, I mean, outlier detection is something we have been looking into in our data exploration stage. And because they could distort our, models and what our models is learning, and they are generally rare events, we always try to find a way to deal with those outliers. If they are not too much, we get rid of them. If they are not too much, sometimes, I mean, again, field expertise is very important here. Sometimes we get together with field experts and they say, okay, oh, are they here? Okay, get them back to here. I mean, just shift those values sometimes. I mean, just like missing values, outliers, dealing with outliers is another stage in data preparation process, even if your objective is not to identify them, but just develop another model. They may be distorting your results because.
I know we're over time. I have one more quick question. I actually have to run really shortly too, but when you mention data pre-processing, are there common techniques for, is that kind of on an ad hoc basis based on the data set and based on the requirements and, you know, the noise in the data, or are there custom, not custom, but regular tools that you're using regularly for data pre-processing? How are you doing the data pre-processing?
In my case, and when I mention about data pre-processing, basically it's not only noise, I mean, get filtering noise, it's some part of it. But when it is about filtering noise, like for example, this was a big problem for me when I was working for defense. We had like sensor information, and it was too noisy. Then I was coming together really with field experts, with avionic people, and say, okay, we need to filter this. But then they were telling me we should use this. There was a filter type, but you couldn't use low pass filter, you couldn't use that filter, but you could use, they said to me, like, no lag filter. So you should filter it out smoothly, but you should, that filtering should not produce any lag in the response, any shift in the response. So those kind of things, and in terms of filtering, was something really I was deciding together with field experts, because physically they know much better than I do in terms of like sensor information. Other things like, for example, I mean, to me, really, data processing is very important stage, and we should always work with cross-functional teams, even in data pre-processing stage. For example, when we have customer segments different like this, I mean, I even go to them and ask beforehand, we think we should have different fault models for this. Because I mean, they know the business very well. They may think that, I think maybe you can first try the same model for all of them and see if it works. Or if you end up with like, this doesn't work for each cluster, they would say, okay, that makes sense because they behave differently. So I mean, coming together with them and just exchanging ideas is really important. Other things are basically dealing with features, outlier detections, missing value, I mean, filling in missing values, dimensionality reduction, all data science stuff, but other part is really about the business, and field experts know that very well.
Thank you. Yeah.
Cool.
So I think I've got to hop off. I've got another call to jump onto, and I think some others do as well. But you know, thank you so much, Mujde, for spending this time to share your wisdom with us. You've clearly spent a lot of time in this field and working with these tools, and it's really neat to just listen to you talk. And thank you also, Shadas, for joining. And as John said, just listening. Yeah. Listening to the two of you go back and forth is fascinating. So thank you for sharing that with us. And I'll turn back over to John.
Yeah, it's always good to be in a room with a lot of smart people, especially a lot of people who are smarter about something than I am. It's a lot of fun. So this has been a great hour. Thank you, Mujde. I really appreciate you volunteering. Thank you for your patience and me getting back to you. And hopefully we're going to have you back again soon to talk about some more stuff with machine learning and you know, data filtering, data cleaning up, you know, figuring out really cool ways to do this stuff. Our next Tech Talk is going to be in 2 weeks. Ryan, I believe you are up for that one. This one here is going to be on interviewing skills and how do you interview? How do you get from where you are at Coding Nomads with all these cool skills and all this great knowledge and get yourself an actual job? So that's going to be a fun one as well. I'm looking forward to that. I'm looking forward to hear what other people have to think about interviewing. I've been on both sides of it, and I'm really looking forward to that one. We have another one right after that with Brandon Geiges, and he's going to be talking about Flask and building APIs as well. And then I don't have anything yet, but we're getting a couple things lined up, and we'll have some more exciting news about that here in the next coming week. So until then, stay safe. If you're stuck in this winter snow like I am, stay warm. And we will see everybody in a couple weeks. Thank you again, Mujde, and thanks everybody for showing up.
Thank you.
Thank you very much.
Thank you. It was great. Thank you.
Thanks, guys.
Thanks, team.
Hey everyone, thanks for watching. If you enjoyed this video, please let us know by liking and subscribing. If there's another topic that you'd like to learn more about, leave us a comment. We would love to hear from you. And if you want to become a coding pro, visit our website at codingnomads.co. See you next time.